Right, guys? Cool. So today we'll be doing our second lecture on the conjugate gradient algorithm. How many of us now have had a chance to take a look at the course notes on conjugate gradient? Shoot-chuck's document, anything. Okay, here's the deal. I've been nervous for today's lecture since Ron asked me to teach this class like 6 months ago. So you should keep me honest if there are problems with indices and so on, because I tend to make mistakes with these, as we've seen in the past, and conjugate gradients is kind of a nightmare of k's and k plus 1s and k minus 1s and all that kind of stuff. But that doesn't mean it's not important, because as we know, linear solvers are used every which way. And maybe I'll even have you implement this one, because you can kind of see what CD is doing. Okay, so we're going to start with a little more review from last lecture than we normally do, because I do think that it's a little bit hard to keep straight in your head all the different things that are going on. So you're going to see a couple repeat slides from last time, and these are basically my ideas of what are the big points from Monday's lecture. And then we kind of stopped in the middle of the story last time, right? We had an inkling of an idea that we could do a little bit better for solving linear systems iteratively, but then we didn't actually tell you how to do it. So that's today's job. Right. So the idea of conjugate gradients and a lot of the related algorithms is that there exists a whole class of matrices, for example sparse matrices, that are easy to apply. Remember, apply and multiply mean the same thing, but are still difficult to invert. Right? So we don't want to run Gaussian elimination because it can induce things like fill, but somehow we still don't expect it to be that much work to solve AX equals B. Right? For example, if my matrix is 99.9% zeros, right, then somehow it's expressing a lot of very simple relationships, but the inverse of that matrix might still be dense. In fact, this is a very common pattern. Right, so what we decided last time is that whereas we started out our discussion of solving AX equals B by kind of just solving it with row, all these row reduction steps and doing it directly, now we have this new set of tools, right, these iterative solvers and these iterative minimization tools to optimize functions, right, to find the minimum of convex and non-convex things. And we'd like to apply those to trying to solve AX equals B. But of course, rather than solve, we have to express our problem variationally. I'm going to keep using this word now. Which basically means that rather than solving AX equals B, we need to write it as a minimization. And in particular, we proved last time that the minima of this function that I have on the projector screen, whatever, these minima exactly satisfy the equation we want, right? So solving AX equals B is equivalent to minimizing this thing when A is symmetric and positive definite. When A is not symmetric and or not positive definite, it is not equivalent to minimizing this function anymore. And we're going to have to come back to that in a while. Yeah? Okay. So what was our strategy? Again, to continue to review from last time, well, we returned to this idea of gradient descent, right? Where you pick a direction from your current estimate of x, and now you have this function f, and you're going to restrict f to the line through that direction, and you're going to minimize along that line. And what we notice is that, well, line search in general is kind of a challenging problem. In fact, line search for this particular function f that we wrote down can be solved in closed form. Right? And we have this formula for alpha on the bottom. Right? So remember that d was our search direction. We're standing at a point x. R is the residual, so that's b minus ax. Right? And if you want to minimize this function g, right, which is just f restricted to the line through x in direction d, yeah, you see that's what's going on upstairs? That is equivalent, or rather the solution to that problem just by minimizing a parabola is this formula for alpha downstairs. And notice that although we motivated this formula for alpha by doing gradient descent on this function f, in fact, our proof really didn't depend on that fact. We could do line search along any direction d. And that's the formula we use. Now recall that in particular when we did gradient descent, our line search direction d coincided with the residual, right? So all these d's got replaced by r's in the gradient descent algorithm. Yeah? Familiar so far? Good, there should be. Okay. So from there, we moved on to defining these things called conjugate directions, right? And we said that the conjugacy is sort of an analog of things being orthogonal, but what we do is before they're orthogonal, we had to rotate them by this factor of the matrix A. And in the end, we define two matrices to be conjugate if V transpose times the matrix A times W is equal to 0. Right? So normally if two vectors are just orthogonal, then you just get rid of the a in between. Yeah? So in fact, orthogonal vectors you could think of are identity matrix conjugate. Yeah? But of course that is very, very heavy language for a very simple concept. And we proved actually a pretty straightforward lemma, which was that if we had a series of A conjugate directions, n of them in fact, and A is an n by n matrix, yeah, then if we line search along the first direction, and then the second direction, and then the third direction, and the fourth direction, by the time we finish the line search along that direction b sub n, we have actually found the solution to ax equals b. Like not approximately, we have actually found the honest to goodness x that satisfies ax equals b. Right? Remember how we did that? We proved that in a different space, this is basically, our function f is basically just the distance from your current point to the actual optimum. Right? And then we showed that optimizing the distance function along orthogonal directions sort of looks like moving just along the coordinate axes. And if you move along n coordinate axes, you get to the origin. Yeah? Okay. So, then, toward the end of lecture, we had one additional clue. So, remember that we defined, gosh, a lot of people are calling me, you define the residual of, so we have this current guess x sub k, which is what we think should satisfy ax equals b, but it doesn't satisfy that yet, because we're iteratively trying to improve our estimate, right? So we define this thing called the residual rk, and here's just equal to b minus ax. And simply by plugging in the formula we have for x based on line search, we showed that you can update your residual just without going back and multiplying a by x each time, simply by subtracting off this multiple of your search direction. Okay. So these were all formulas we proved last time. They're also proved in your notes in case I likely made mistakes in class. Yeah? So that's sort of our story so far. And finally, using this proposition, we proved a useful statement, which is that if we do gradient descent on f, and remember when I say f, I'm not talking about just a generic function f, I'm talking about specifically that quadratic function that we wrote down on the first slide. Right? And when I do gradient descent on that function f, and I look at the span of all of the residuals, that was equal to the span of the first residual, a times the first residual, a squared times the first residual, and so on. Yeah? And the way that we prove that is actually just using the second formula on the screen here, right? Because remember that our search direction, if we do gradient descent, is just equal to r, right? So in fact, this looks like rk plus 1 equals rk minus alpha ar, right? So in particular, it's a linear combination of a residual and a times a residual, yeah? So that induces another power of a every time you run the formula, yeah? So that was sort of the high level idea. Okay. So hopefully you all agree with me so far. If not, you can take these statements for what they are and look up the proof later. Yeah? Cool. All right. So unfortunately, because of the lemma, we notice a really bad property of gradient descent. Right? So gradient descent, remember our search direction is exactly this residual, and now we've written down a subspace that your residuals and or your search direction, because they're one and the same in gradient descent, we wrote down a subspace of Rn that spans the current set of residuals, right? And what we'd really like, what would be a really cool property for one of these iterative algorithms is to say, basically what I'm doing is I'm adding, another vector to my subspace during each iteration, right? And maybe somehow I'd hope to be able to minimize f over the entire span of these vectors, right? So every time I introduce another vector, the minimization problem changes, but maybe it's only a shift around from the last guy. But sadly, although that would be a very nice story, that is not what is going on in gradient descent. In fact, it could be the case that there exists some v in the span of these vectors that we've seen so far that makes f even smaller than your current iterative of gradient descent. In particular, this means that gradient descent can cycle forever without actually touching the minimum of your function, and it decreases the value each time. And it does converge. We did prove that, but we didn't prove that how long it takes. Okay? So this is a very bad property. And in fact, when you have these matrices with this very wide elliptic shape, right, these poorly conditioned matrices, then what happens is gradient descent zigzags into the origin. Not so good. Cool. All right. But if this property did hold, right, Well, what would happen at n steps? Well, the span of r0, a times r0, dot, 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 all the way to, what, a to the n r0, that's just Rn, right? You have n linearly independent vectors. So in fact, what you would be doing is just minimizing f over all of Rn, and you'd be done. Right? So this would be a really cool property to have. This is kind of a weird way to do mathematical exposition, right? I'm sort of writing down like my Christmas list of all of the things I'd like for my iterative solver, and then just kind of being sad that gradient descent doesn't have any of them. And obviously I'm doing this sort of with some intelligent design, right? I mean, it's pretty clear that what we're about to introduce will solve all of these problems and more. Yeah? Okay. So, assuming we could somehow solve all of these problems, our algorithm would look something like what I have on the screen here, right? Somehow we would generate a new search direction, right? This is very similar to gradient descent, right? You somehow generate a search direction. It's no longer going to be the gradient descent search direction because we decided that's a bad strategy. And then we're going to line search along that search direction, and remember our formula for alpha still holds. Right? Our direction is going to be v, by the way. And then you're going to update your estimate, xk, based on the previous estimate and the new alpha you just computed. And finally, you'll update your residual using that formula you wrote down. Yeah. So in fact, you know, when you look at listings of algorithms like conjugate gradients, like if I removed all the decorations on the left here, this would be completely like obtuse, right? But in fact, it's kind of intuitive what's going on here. Right? You just sort of, you go down a line, you change where your toes are pointing, you reevaluate the situation, and you keep moving. Right? That's all that's going on. These are pretty simple methods. Cool? Okay, so I'm going to replicate these steps on the board because I think it's useful to keep them in mind while we do a little bit of extra math. So again, we're going to generate the direction VK. Right? And so far we don't know how to do this, right? We'd like these directions to satisfy some nice properties, and we're going to figure that out in a second. Then what do we want to do? After that, we're going to do some line search. And this is just alpha k. I always get these formulas wrong. V k transpose r k minus 1. Times v k transpose a v k. Yeah. As a third step, we're going to update our estimate, right? Alpha k, vk. By the way, something that is easy to get wrong, and I got wrong in my first 25 drafts of the course notes, is this formula right here, which seems innocent enough. But the problem is that you have to keep track, you have to decide which of the k's you're currently dealing with, right? So for me, I'm going to assume that my rk and my xk move in lockstep, meaning that at every point in time, the formula, the residual equals b minus ax, this will always be true when you match all the indices, okay? And then the tricky part is that the search direction vk is going to come from the previous residual, right? So vk is going to look sort of like rk minus 1, right? And so it's easy to forget that the kth search direction is the k minus first residual, okay? So I'm going to point that out now, and I'm going to screw it up in about 2 minutes. So when I do that, now you guys will all know to stop me immediately, okay? And finally, we have one more step in this algorithm, which is that we do the residual update, which is rk equals rk minus 1 minus alpha ka bk. Yes? By the way, I could have used this formula here. That would have been perfectly fine, in fact equivalent mathematically. We're going to find that this residual update is convenient numerically because what we're going to do is we're going to reuse this product in more than one step. So that's going to save us a matrix vector multiply. But there is a problem, which is that we have all these iterative updates, right? We keep taking our last estimate of the residual and then just changing it incrementally. And remember that if we're on like a grown-up computer and we're using IEEE floating point and all these things that I don't like to talk about, right? There's some odds that this subtraction and this multiplication and so on are not 100% right. Yeah? So in fact, if you read Shuchuk's document, what he recommends is every 50 iterations, use this formula just to fix your residual in case it's kind of drifted away numerically. Right? And in fact, back in the days when we had bad processors and we couldn't do like 4 bajillion decimal points of floating point arithmetic when we were running algorithms like this, people were very suspicious of conjugate gradients, especially because of this update step, because it tended to drift very quickly. Right? If you write, especially if you write this in like fixed point math, you can be totally hoaxed. So this is just a good drawback to keep in mind. Okay, so hopefully everybody kind of understands the philosophy here. I know I'm repeating myself a bit, but I think it's very easy to get lost in all of these symbols, and I want you to keep in mind that in fact conjugate gradients is actually a pretty straightforward procedure, despite all these documents that say that it's agonizingly painful. Yeah? Okay. So greedily, what do we want? Speaking of repeating myself, we'd like to somehow find n conjugate directions, right? Because then we know we will terminate in n steps, right? N plus 1 steps of conjugate gradients will do nothing because you will have already solved ax equals b. Yeah? In fact, they'll divide by 0. We'll see in a bit. And we'd like the span of our first k, so for each k, right, if we're in the kth iteration, we'd like the span of the search directions we've seen so far to look like the span of the first residual, a times the first residual, and so on, right? Because then it sort of parallels what gradient descent is doing, right? Otherwise, we're going to have to do a lot of work to justify why the heck we were changing things so much. And if we have these properties, what would happen? Well, for one thing, we would converge in n steps. That's clear from these lemmas we've written down. And additionally, we would always do better in every iteration than gradient descent. Why is that? Well, remember our proof of why we converge in n steps, right? We showed that, in fact, what's going on here is you have some estimate z1, actually I should write a couple of coordinates, z2 all the way to zn of the root. Right? And if you rotate your coordinate axes, then really you're doing line search along the first guy, and then line search along the second guy, and so on. Right? Hopefully we remember this proof from last lecture. Right? And then what happens, right, is eventually you want this to go to your actual root, or yeah. Yeah. And if we line search along the first coordinate axis, and then the second, and then the third, then basically what ended up happening is that the first iterate stuck a star here, the second iterate stuck a star here, all the way to the last guy put a star there. Yeah? Well, look what happened. In the second iteration, did I change the first coordinate? No. Right? So in fact, I remained optimal in the first guy and added optimality in the second. Yeah? So in particular, what this means is that now, after 2 iterations of gradient descent, I am now optimal in span of the first 2 standard basis vectors, right? And when we undo all of these coordinate changes that we did last time, that's the same as being optimal in the span of your first 2 search directions, right? So conjugate methods have this really nice property, right? That if you keep searching in these conjugate directions, you're sort of just adding dimensions along which you're optimal, right? Gradient descent does not have this property, right? In other words, if I move along the latest residual and do even a nice closed form line search, I can lose some of the work that I did before and become suboptimal in that subspace. Cool? All right. Oh, and by the way, so the second point here is saying we're always better than gradient descent because in fact, we are 100% optimal in this span, whereas gradient descent, you're in this span, but you're not necessarily optimal. Yeah? Okay. I know these arguments are hairy, but thankfully I think they're kind of they come in nice independent little packages. So if anything is really confusing to you, you can go back and study it, and as long as you believe it, then we can carry on. And if you are stuck, you should stop me and ask. Okay. So let's say that we're searching along conjugate directions that somehow God has given us for now. Right? Obviously our last job is going to be to actually generate these directions. But anyway, God is handing down conjugate search directions somehow, and now we have this quadratic function f, and we take his gradient, right? Remember his gradient, in fact minus his gradient is b minus ax. That hasn't changed, right? It's still the same function f. Yeah? Then I claim that if I've been searching along a conjugate search directions, in fact the gradient of f is orthogonal to all of the search directions you've seen so far. Now why is that? So remember what the gradient is doing. Or I guess since we're minimizing f, remember that minus the gradient of f is the direction in which f is decreasing the most. Yeah? So in particular, I'm guaranteed that if I step in minus grad f, and by the way, we'll assume that it's non-zero. If it's 0, we'll just stop our algorithm because we're done. Yeah? But if the gradient is non-zero and we step in the minus gradient direction, what happens to f? Does it increase or decrease? Dave, what happens to f? Remember, we have the algorithm is called steepest descent. It decreases. Yeah, f decreases when I move along the negative gradient direction. Nice. And so in particular, what would happen if grad f were not orthogonal to these search directions? Well, it would mean that there is some search direction I could walk in and decrease f a little bit. Yeah? But that's against the rules, because what I just told you in the previous slide is that we are optimal in the span of the first k search directions, right? So in fact, what I just sort of proved to you in words, and if you write it out, it's no more enlightening, is that in fact minus grad f, and remember again that grad f evaluated at x is nothing more than b minus ax, yeah? That this thing is always orthogonal to the search directions you've already used. Cool? By the way, this is the first instance where when I was writing your course notes I screwed up these subscripts. Because v1 through vk, right? So what is xk? It is the result of searching, well, so look what happens. So xk includes vk, right? So xk is the result of searching through v1 all the way through and including vk. So this is correct. So grad f at vk is the gradient after optimizing along these k directions. You can see how it's easy to screw this up. Okay. And here's the hairiest little bit of the conjugate gradients algorithm, and from here on it's going to be way less technical, which is that, in fact, this statement upstairs implies that for each k less than I, the ith residual dot product, this is not the A product, the dot product of the ith residual and the kth search direction is equal to 0. Okay, so how can I prove this? Well, this is where I'm going to screw it up. Actually, no, I'm sorry. I'm going to screw up the thing in the next slide. This thing is obvious, right? Because the ith residual is nothing more than gradient of f. I got excited, then I realized this isn't the hard form. Yeah, so remember orthogonal means dot product equals 0. Yeah, so vk is what it is, and then we're saying for each residual. Actually, I swapped the i's in the case. That should be rk dot vi. Have I confused you yet? David?
I just have a question. So, like, is ri the residual after you've stepped?
Yes. Yeah. This is why it's easy to screw this stuff up. Yeah. So the residual is perpendicular to all of the search directions that come before it. Okay. Cool. So here is the difficult result. Not difficult, but just easy to get wrong. Which is that, in fact, the A inner product of VL and RK, right, the Lth search direction and the Kth residual is equal to 0 whenever L is less than K. Remember, I warned you guys in the last lecture we have two different inner products. Yeah, do you remember what they are? So we have just the usual dot product x dot y, right, which we usually write as x transpose y in this class. Yeah. And then now we've introduced this second guy, right, this A product, right, which you guys secretly saw a few homeworks ago on that problem nobody liked, and that was x transpose AY, right? These are both inner products. This one is a dot product. Yeah. So now, remember our last slide was about dot products. Now I need to characterize inner products because what we want at the end is that this inner product equals 0, right? That's going to give us conjugacy. So we're going to start to prove this one step at a time. So how are we going to prove this fact? I'm so looking forward to next week. Next week is easy. Okay, so we have VL, RK, and this is the A inner product. And just to remind you guys, we have L is strictly less than K. Okay? When they're equal, something else is going to happen. Okay, so what happens when L is less than K? Well, by definition, we know that this is the same as VL transpose A, RK. Right? That's the definition of this inner product. And now, a usual strategy for writing proofs about the conjugate gradients algorithm and gradient descent and all these kinds of things is when you don't know what you're doing, you just start plugging in one of your recursive formulas for vectors that you have. Right? And in particular, you know that L is less than K, so you're probably going to want to decrement this K over here. Yeah? This is just a sort of, I'm trying to help you guys think about how you might approach a proof like this. If just for instance, it might show up in your homework. So, right, so we have VL transpose A, and then we have a formula for RK, right? We derived that already. He's equal to RK minus 1 minus alpha K A BK. Yeah? Remember, this is the same formula I keep writing down. And now let's expand this minus sign. And what do we get? Well, we get VL RK minus 1 A inner product. Yeah. And alpha K VL VK A. Oh, cool, right? Because the A inner product was a VLA this and a VLA that. Oh, oops, did I have a, there should be an A squared there. Oh no, oh, and thus it begins. But that's okay, okay, cool. Alright, so my lecture notes are a little bit wrong. We'll just do that. Cool? Alright, I warned you guys this is gonna happen. Okay. So, right. So, okay. Cool. Okay, so I want to argue to you that both of these terms is equal to 0. So how are we going to do that? Well, sorry guys. Okay, fine. Okay, so the basic argument goes like this. This is always embarrassing when this happens. I never argued these before class. So we can catch this one. Right. So the RK, what's going to happen here is that you have an A RK minus 1. So let's start with the first term. Yeah. Is it okay if I write this? Okay. I knew this is going to happen. I was so happy with myself because Monday's lecture I don't think we screwed up any of this. Okay. So right. So remember that this thing really looks like what? He's VL transpose A RK minus 1. Yeah? Okay. So now let's take a look at what happens, right? So A times RK minus 1, right? He is in the span of, well, A times the span of what? Well, RK minus 1 is certainly in the span of R0 to RK minus 1. And remember that we claim that is the same as R0, AR0, and you can go back and double check when we write down the conjugate gradients how this fact is still true, all the way to A to the KK minus 1 R0. Yeah? Just because this guy is in the span of all the R's, right, then I made it bigger. Right? So, in particular, this thing, right, I can move the K on the inside and stick another thing into the span. We're just going to keep making it bigger. Right? This thing is a subset of the span R0 to A to the K R0. Yeah? I just moved the K on the inside and added another R0. Yeah? And so now what can we do? Well, this thing is equal to the span of R0 to RK. Right? This is by our previous relationship. Okay. And now remember our previous slide. Yeah? What did we show? We showed that for all K, that when you take a residual and you dot product it with the search directions you've seen so far, you get 0. Well, look what happened. This guy, right? This object here is in the span of the residuals. Right? This is the search direction, and this whole thing is a dot product. right? So in particular, I just proved to you that this number is just 0. Yeah? Right? Because you can, I see a couple of furrowed eyebrows. Because you can write ARK minus 1, right? That's this thing that I just expanded here, as some linear combination of these residual vectors, right? Because it's in their span. And every single term in that linear combination, every single dot product with one of these b's is going to give me 0 by what's on the previous slide. Now, this leaves us with what happens with search direction here, which is an excellent question. What did I do wrong? Oh, right. Okay, fine. So, can I do this? You know what? I might have to get back to you on why the second term is 0, because there's a typo in my notes, and that's embarrassing. Yeah. Actually, I guess you could. Oh, right. Okay. Nah. Yeah, we're not going to worry about it. I'm sorry, guys. I will come back to this argument rather than use your class time. Okay? Unless anybody has some brilliant idea. It basically has to do with your search directions being A orthogonal, but accidentally I put an A squared in there and now I'm confusing myself. But I'll go back and fix this. But it's nothing major. Basically, you when L is less than K, this term is also 0, and I will double check this for you when I get home. I apologize for this. These things happen. And but what does this mean? Well, other than it meaning that your instructor is a horrible human being, it means that if I wanted to take my current residual RK, and remember, how did I do gradient descent? I took my residual from the last iteration and I used that for my current search direction, right? But now I want my search directions to be A orthogonal, so in particular, what am I going to do? I'm going to take my last residual, I'm going to project out all of the search directions I've already seen already, right? In fact, you're going to do that using the homework problem. That's the very first thing on your homework, I think 1B this week is sort of in general how to project stuff out, right? But the idea here is just Gram-Schmidt. Remember how Gram-Schmidt works? You have a whole set of vectors and you're trying to orthogonalize them. And how do you orthogonalize them? Well, you start with the first direction, you leave them alone, right? So we're going to initialize CG just by searching along the first residual. Yeah? And then the second search direction, we're going to start with the residual, and then we're going to project out the first search direction. Right? And then the third search direction, we're going to start with the residual again, and we're going to project out the first and the second search direction, and so on. Right? But look what this claim tells you, if you're a better mathematician than I and actually managed to prove it, which is that, in fact, you're already orthogonal with respect to the inner products we care about. Remember, that's not a dot product anymore, it's this A thing, right? This A inner product. You're already orthogonal to everything more than 2 steps ago. Right? Because what am I going to do? Well, I'm going to generate VK plus 1, right? He comes from RK, right? The previous residual minus a projection onto the first K search directions, using the right A inner product. Yeah? So in fact, what we just showed is that all terms except for the very last one are already 0, just automatically. We get lucky. Yeah? This is actually an amazing fact about life. All right? So let's see what this tells us. Yeah? In particular,